Okay, so what we talked about is that what we have seen is computing this page rank for a very small set of pages. We only had 3 pages, Amazon, Yahoo, and Microsoft, which was how a web looked like in 1938. If we are to compute page rank for all the pages on the internet, and we have trillions of pages, then how does that look like? So Google computes the page rank of a trillion pages at least. How much space would that take, and how long does it take to compute something like that? So the page rank vector, if we are using real numbers with double precision, then it will take 8 terabytes to compute the page rank. And so the matrix of the web has 2 special properties. One of the properties is that this matrix is very sparse. So the matrix is sparse, the average, because it has lots of zeros and very few ones, and the reason for that is the average web page has about 10 links that come out of it. And another thing is that another property is each column has a single value, 1 divided by the number of outlinks, and that appears wherever the column is not 0. So we can take advantage of this sparse matrix, and instead of recording the entire matrix, we're just going to record a list of the values that are not 0. So for each column, we will store the number of outlinks with non-zero values. And so if we do this computation, then the matrix of the web will require about 84 terabytes to store. This number here is just an integer, and this number is for the average links that a page has, which is, it has about 10 links out. So that will take 8 bytes per row number. Of course, if we were to compute a matrix multiplication of this size in a single computer, that's not going to work very well, so we could divide this among multiple computers and use a cluster of computers to compute this. So we will divide these page rank vectors into stripes of equal size, and the size is k. And the matrix will be divided into squares, and each square side is the same length as these stripes that we create. K will be chosen as a size that can fit into the main memory of a single machine, if that's a commodity cluster of commodity machines. So this type of computation can be done in the cluster in many machines in parallel. If the k is equal to 3, then this is what the matrix will look like. There are 3 pieces per row here, and the size of the square is of a stripe of length 3. So in this at one time, we need to keep in main memory only the pieces that we are doing the computation for. So these will be the pieces that will be kept in memory. Wi and Wj, so whatever row and column we are computing at that particular time. So each column of a block is represented by the number of non-zero elements in the entire column, and that has the number is the number of links that it has out to other pages, and the list of the block only that have the non-zero values. because, as we said, most pages will not point to all other pages, but only to a few of them. So the ones that are not zero will be used divided by the number of links that they contain. So for each column, we will store n with each of the blocks in the outlink. That whatever link that it is going to. So whatever block has the row to which the link is going to. So we are pretty essentially dividing this huge matrix into manageable pieces that can fit into main memory of a single machine. Now, other than that multiplication, we also need to compute the tax, because we mentioned that we are having introduced this taxation factor into the PageRank in order to prevent spider traps and affecting the PageRank by this kind of spider traps and dead traps. So neither of so we can introduce this taxation into the computation and still we will follow the same method. So in MapReduce, we are doing just matrix vector multiplication MapReduce. Because the matrix is sparse, we can treat it as a relational join. Another way is to use a number of jobs. Each of them will multiply a row of the matrix blocks by the entire vector. The main memory we use to hold one stripe that will be produced. And then we will read this one stripe into main memory at a time, and the block of the matrix that needs to be multiplied by this vector one at a time. So there will be several jobs, each one working on a piece of the matrix. So for a particular job, we will call W part of the matrix and the vector that we're multiplying it into the main memory. And next another job and another job. So we will have multiple jobs to solve this PageRank computation in a parallel